In this video, we're going to go over some practice problems from the material covered this week. So that'll be sections 2.2, 2.3, 2.4, and 2.5. So starting with section 2.2 here, what we want to do is find the slope of the line passing through these 2 points. Now we know we can easily find the slope of the line given 2 points on that line using our slope formula here. And that says m is going to be equal to y2 minus y1 over x2 minus x1. Now, these x sub 2 and, or y sub 2 and y sub 1 and x sub 2 and x sub 1 are given from these coordinates here. So if this is my first ordered pair, this is going to be my first x and my first y coordinate. So I can call this x sub 1, y sub 1, and this guy will be x sub 2 and y sub 2. So now we're just going to plug this into our formula here. Our y2 is 5. Then we're going to subtract out whatever our y1 is. Our y1 is negative 3. And then on the bottom, we have x2 is negative 1, and we're going to subtract out our x1. And our x1 is minus 2. So here we're going to get 5 minus a negative 3, so this becomes a positive. And similarly in the denominator here, we have negative 1 minus a negative 2, so this minus and this negative here is going to become a positive. So we're going to have 8 over 1 here. So the slope is just going to be 8. Now, something I wanted to point out here is that it doesn't matter in which order we label these pairs. We could also label this guy as x2, y2, and x1, y1. What we do is we'd still plug in these values into our slope formula, and it's not going to change the value of our slope. So in this case here, our y2 then would be negative 3. And we're going to subtract out what our y1 is, and our y1 is going to be 5 here. Then on the bottom, our x2 is going to be negative 2, and we're going to subtract out our x1, which is going to be a negative 1. This will give us, we have negative 3 minus 5, which gives us negative 8. And on the bottom here, we have negative 2 plus 1. So this will give us negative 1. The negative in the numerator and the denominator are going to cancel, so we just end up with positive 8 as our slope, and that's exactly what we had in this case. So it doesn't matter which way you label them, as long as you make sure your x's correspond to your x coordinates and your y correspond to your y's. All right, let's move on to question 51 here. What we want to do is find the slope of this equation here, and we're going to do that 2 different ways. First, we're going to find any 2 points that lie on the line, and we can use those points to find the slope using this formula here. And then the other way, what we'll do is we'll solve our equation for y. So for part A here, we want to just find 2 points that are going to lie on this line, and 2 easy points are just going to be the x and y intercepts. And I say that these are easy points to find because we're setting one of the variables equal to 0. So when we do that, it's going to cancel out an entire term. And I'll show you that in a minute. So we want to find our x and y intercepts. So for our x-intercept here, we're going to set y equal to 0 here. So we're going to plug in 0 to this guy, and this whole term is going to go away. We're just going to be left with 3x is equal to 12. Now solving for x, this is going to give us x is equal to 4, and so our y-intercept is going to be 4, 0. Now on the other hand, for our y-intercept here, we're going to set x equal to 0, so this whole term will go away. We'll get 4y is equal to 12, which tells us y is going to be equal to 3. So our y-intercept is going to be 0, 3. Now we can easily find our slope using this formula here. So we're going to label our points. This will be x sub 1, y sub 1, x sub 2, and y sub 2. So m then is going to be, we have y2 minus y1 over x2 minus x1. Which gives us negative 3 over 4. And then again, just to emphasize, we could have reversed the order of these points here, and we'd still get this minus 3 over 4, just like we showed in the first example. All right, now for part B here, what we want to do is find the slope by solving the equation for y. So I'm going to rewrite the equation here. So we want to get y completely by itself. That's what it means when we're solving for y. We'll subtract 3x on both sides. we'll be left with 4y is equal to 12 minus 3x. And then dividing by 4 to get y completely isolated here, we're going to get y is equal to 12 over 4 minus 3 over 4x. Now something to point out here, notice we have this minus 3 times x here, and then we're dividing by 4. You might want to write this as minus 3x and then divided by 4. That'll be the same thing. We still have this 3 times x divided by 4, but we're writing this fraction completely in front of this x just to emphasize that this is the coefficient of this variable. All right, we also want to rewrite this equation so that our term with our variable comes right after our equal sign here. So we get minus 3 over 4x, and then we're going to add this term here. So I'm not changing the signs of these terms. This is a positive, this is a negative. I'm just reordering them. 12 divided by 4 is going to give us 3. Now the reason we're reordering them is because of where this term lies. The coefficient in front of this variable here is going to be our slope. So this minus 3 over 4 is our slope, and that's exactly what we got in part A here. So there are multiple different ways that we can find our slope. So just to emphasize, m is minus 3 over 4 here. All right, let's move on to question 71 here. So this is a graphing question. What we want to do is now graph a line, and this line is going to pass through this point and has this slope. So first piece of information is this point, so let's plot that. We have negative 1 comma negative 2, so that point's going to lie right here. All right, now we can plot some more points using this information here. This m is equal to 3. This is going to be our rise over our run. And this is not a fraction here, but remember, 3 is the same thing as 3 over 1. So in this case, our rise is going to be 3 and our run is going to be 1. So what I mean is, from this point, we're going to go up 3 over 1, up 3 over 1, and continue on in this fashion. So that's a point, that'll be a point, and this will be a point. Now going up 3 and over 1 is going to be the same thing as starting here and going over 1, but in this direction, so going left 1 and down 3. That's not going to change the sign of our slope. This is still a positive slope, but we're moving in the opposite direction to get the other points. Notice from each point we're still going up 3 over 1, and so on. So this line is going to look something like this here. Now, for these next two examples, we just want to determine whether the following pairs of lines are going to be parallel or perpendicular to each other, or neither. Now, in order to determine this, we need to find the slope of each of these lines. The slope is going to tell us this information. And so, as a reminder here, two lines are going to be parallel if they have the same slope, or two lines are going to be perpendicular if their slopes are opposite reciprocals of each other. So opposite just means different sign. So for example here, if our slope was 2/3, the opposite of that would be minus. Because we have positive 2/3, the opposite would be a minus. Now the reciprocal portion is when we flip our numerator and denominator. So we started off with 2/3, and then the opposite reciprocal would be minus 3 over 2. Now, if we started off with a negative slope, then the opposite sign of our negative would be positive. So another example, if we had negative 1/2, the reciprocal of this would be positive 2 over 1, or just positive 2. All right, so let's look at these two examples here. What we're going to need to do is find the slope for each of these lines here. And the easiest way to do that is just going to be to solve for y like we did in the last example. So I'm going to subtract 4x on both sides of this equation here. This tells me y is going to be equal to minus 4x, and remember the slope is going to be the coefficient of our x variable, so it'll be negative 4 in this case. Now for the next equation, we want to get y completely alone, so we're going to divide by 2 on both sides. This will give me 5 over 2 times x minus 8 over 2, and that's going to be equal to y. Now I just want to reorder this. Typically we have y on the left-hand side of our equation. So I'm going to get y is going to be equal to 5 over 2x minus 8 over 2, which just gives us 4. Now in this case, our slope m is going to be equal to 5 over 2. All right, now looking at these two slopes, they are not the same, so they're not going to be parallel, but they're also not opposite reciprocals of each other. So in this case here, this is going to be neither. The pair of lines in this example are neither parallel or perpendicular. All right, so let's look at this example here. Again, we have these two equations. The easiest way to find the slope is just going to be to solve for our variable y. So for this first equation, I'm going to subtract 2x on both sides. This will give me 5y is equal to minus 8 minus 2x. And then lastly, we'll divide by 5 to get y by itself. So y is going to be equal to minus 8 over 5 minus 2 over 5x. And then I'll just reorder this. So we have our term x right after our equal sign here. So this will be minus 2 over 5x minus 8 over 5. So in this case, our slope is going to be minus 2 over 5. All right, now again, just emphasizing, we started out with this minus 2 times x, and then we divided by 5. Writing this minus 2 over 5 in front of our x is the same thing as multiplying by 2 and then dividing by 5. We're just writing this number by itself to emphasize that that is the whole coefficient of x. All right, doing the same thing for this equation here. We want y completely alone, so we're going to divide by 5 on both sides. We're going to get this on the left-hand side, and then just reordering this so that we have y on the left-hand side of our equal sign. We're going to have y is equal to minus 2 over 5x plus 6 over 5. All right, and in this case, our slope is going to be minus 2 over 5. These guys have the exact same slope, so these two lines are going to be parallel to each other. Now, just as a side note here, if we're looking for a line perpendicular, so if we're looking, for example, let's take this line here. We have this slope minus 2/5, so a line perpendicular to that line would have slope opposite reciprocal, so this will be positive 5/2. So just as a side note there. All right, so now we're going to move on to some questions from section 2.3 here. So first for question 17, what we want to do is we want to write an equation of a line given this information here. So we have a line with slope negative 2/3 and b is going to be equal to 4/5. So we have a slope and we have our b value for our y-intercept. So we're going to use an equation of this form here, mx plus b, where m is our slope and b is this value here. So just plugging this information in, we're going to get minus 2/3, that's our mx, plus our b value, so 4/5. So that would be our equation given that information. Now, just something to note here. Another way to present this information that you might see in the homework questions would be, we would just label or say exactly what our slope would be. So slope would just be minus 2/3, and our y-intercept would be given by 0, 4/5. Okay, so remember our y-intercept is always going to be 0, whatever this b value is, because remember to find our y-intercept, we're plugging in 0 for x. Okay, so if you see in the homework the information presented in this way, it's the same thing as this here. All right, let's look at 49 here. Again, we want to write an equation of the line, but now given the fact that the line passes through these 2 points. So the first thing we're going to need to do is find the slope, and we can do that easily because we have 2 points here. So we'll label these guys and find our slope. Our slope is going to be, we got 8 minus 4 on the top, and then 5 minus 3 on the bottom. So this will give us 4 over 2, which is just 2. Now again, we can use our y is equal to mx plus b here. And what we can do is solve for our variable b. In the last example, we were given a slope and our b here. In this case, we found our slope, and we can also find this b using one of these points here. If we were to plug in our x and y coordinates into x and y here, and then plug in our slope, we're just left with one variable that we can solve for. So plugging this in, we're going to get 4 is equal to 2 times 3 plus b. So that gives us this here, and then subtracting 6 on both sides, we're going to get that b is equal to negative 2. So this tells us y is going to be equal to 2x and then minus 2. Now something I want to point out here is that we could also use our point slope form, right? Once we find our slope, we have at least one point, so we could easily use this point slope form here. Remember, these sub ones here are going to be one of our points, and we can use either point to plug in. Don't get confused with this x sub 1 and this x sub 2 notation here. In this point slope form, all this means is that the things with the subscripts are going to be plugged in, and you can use either point. As long as you have one point and your slope, you can use this. So let's use this same one here. So we're going to get y minus 4 is going to be equal to 2 times x minus 3. Next thing we'll do is we'll distribute this 2 here, and then we'll just solve for y. So, or adding 4 on both sides, this gives us y is going to be equal to 2x minus 2. So notice we get the same thing. You can use either one of these equations here to write the equation given this information. It just depends what you're more comfortable with, but as long as you have this information, you can use either one. All right, let's look at another example here. For 37, for this equation given, we want to first write it in slope-intercept form, give the slope of the line, and then give the intercept. Okay, so remember, slope-intercept form is y is equal to mx plus b. The naming conventions of these equations are nice because in slope-intercept form, you have a slope and you have an intercept. In point-slope form here, you have a point and then a slope. Okay, so that's how you can identify them. Now for a here, we want to write this equation in slope-intercept form. So first thing we're going to do, because remember we want to solve for y, is we're going to subtract x on both sides. This will give us 2y is equal to minus 4 minus x. And then to get y completely isolated, we'll divide by 2 on both sides. So this will be this here. And then writing it in our y equals to mx plus b form. So our first term is going to be our term with our variable x right after our equal sign here. We're just going to reorder these two terms here. So remember, we want to emphasize what our coefficient is in front of our variable x. In this case, it's going to be 1/2, right? If we pull this x out here, we're just left with a 1 in the numerator. So this will be minus 1/2 x, and then we're going to subtract out 4 divided by 2, which is 2. So that is that equation in slope-intercept form. Now for b here, we just want to identify the slope. We know the slope is going to be m, which is minus 1/2 in this case. And then for c here, we want to identify the intercept. Now, the intercept is going to be b here, but as an ordered pair, we're going to write it as 0, minus 2. All right. And then lastly, for section 2.3, let's do question 75 here. We again want to write an equation of a line given this information here. So this line needs to pass through this point, and it needs to be parallel to this line here. Now we know if a line is going to be parallel to another, they need to have the same slope. So the first thing I'm going to do is figure out what the slope of this line is. Because if we want a line that's parallel to this, we're going to have the same slope, and once we have a slope and this point, we can easily write the equation. So let's find the slope of this guy. The first thing I'll do is add x to both sides, because remember we want y to be isolated. Now dividing by 2, we're going to get y is equal to 10 over 2 plus x over 2. Now rewriting this is going to be y is equal to 1/2 x plus 5. So in this case, our slope here is going to be 1/2. Now we have a slope and we have a point, so we're going to use point-slope form. All right, plugging in our given information, we have y minus. Now we have to be careful with our signs here. Point-slope form is this here. These minuses are there to stay. So we're going to take y minus whatever our y value is, and this is minus 2. So we have to plug in this whole minus 2 in for y1. Now we know our slope is going to be 1/2, and then we have x minus our x1 value. So we're also subtracting out a negative 2. So this minus a negative here gives us y plus 2. And similarly for this guy here, we get x plus 2. Now to solve for y, we'll distribute this 1/2 on both sides first. So we'll get y plus 2 is going to be equal to 1/2 x and then plus 1. Then lastly, we'll subtract 2 on both sides to get y completely alone. So y is going to be equal to 1/2 x minus 1. All right, so this would be how we write an equation given that information. Now, in section 2.4, what we're going to be doing is graphing inequalities or pairs of inequalities. So we're going to start with question 16 here. What we have is 3x minus y is less than 3. And what we want to do is solve this inequality by graphing. So we want to figure out for which values of x and y will make this statement true. Which values for x and y, if we plug it in, will be less than 3. So we're going to start off by graphing our boundary line. Now this line is going to be 3x minus y is equal to 3. And what this line does is it's going to separate our coordinate plane into different regions, where this is going to be less than 3 or greater than 3, or on this line, this is going to be equal to 3. So first thing we want to do is graph this here. And what we'll do to graph this is we'll solve for y, because then we can easily see what our slope and intercept is going to be. Now notice we have a minus y here. What I'm going to do to solve for y is actually just add it to this side here. So then I'll end up with a positive y. Now in the same step, I'm just going to subtract 3 at the same time. So that when I solve for y, let's just write it down here. I just solve for y in one step. I'm going to get y is equal to 3x minus 3. Okay, so solving for y in this case is just a 2-step process. So what I'm doing here is just doing it in one step, so I only have to write it down once. Okay. Now, we can easily see here that our y-intercept is going to be 0, negative 3, and then our m is going to be positive 3. So we're going to use this to graph this line. This is going to be our y-intercept here, and then to plot several other points, we're going to go up 3 over 1. And continue this process here, just like we did on the graphing example in section 2.2 at the beginning of this video. So our line, these are all going to be points on our line. Now what I'm going to do, and this is what the book does also, is I'm going to graph this line here as a dashed line. And the reason being is because if you go back to our inequality here, we're saying 3x minus y is less than 3. So we're looking for solutions that will make this true, but we're not looking for solutions that will make this equal to 3. All the solutions on this line, as we saw, remember our boundary line is 3x minus y is equal to 3. So that means everything on this line here is going to be equal to 3. If we were to take a coordinate, for example, here, this is going to be 1, 0. We plug in 1 for x and 0 for y, we get 3 is equal to 3. Okay. In this case, we're not looking for the ones that'll make it equal, we're looking for the solutions that'll make it less than. So that's why we have a dashed line here. Now, all we're going to do in this question, now that we've graphed this line here, is highlight the region where this is going to be true. And this is going to be everything to the left of this line here. So all of the solutions for this inequality are going to lay here, to the left of this line. All of these guys are going to make this inequality less than 3. And what we'll do is we can use a test point So we can pick some ordered pair in this region and make sure that it does make this statement true. So for example here, let's pick negative 1 comma 1. Let's pick this test point. So we'll highlight that one there. So plugging this into our inequality here, we're going to have 3 times negative 1 minus 1 is less than 3. This is going to be negative 3 minus 1, which we know is going to be less than 3 because this is negative 4. Okay, so that is a test point in this region that'll make this inequality true. And so that's all we're looking for in this case. All right, let's look at question 24 here. We're going to do the same thing. We want to figure out which values of x and y will make this true. We're going to start off with our boundary, which is going to be 3x plus 4y is equal to 12. And we want to graph this line. So we're going to solve for y. First thing I'll do is subtract 3x on both sides. This gives me 4y is equal to 12 minus 3x. Now solving for y completely, we'll divide by 4 on both sides, and so this gives us y is equal to minus 3 over 4x, plus we have 12 over 4 here, so that'll be plus 3. So here, our y-intercept is going to be 0, 3, and our slope is minus 3 over 4. All right, so let's plot this. So 0, 3 is our y-intercept, and since our slope is negative, our graph's going to face this way, right? In the last example, this was a positive slope, so it was facing that way. Now to graph this, we're going to graph more points. So we know we're going to go up 3, and then we're going to go left 4. Since this is negative, we're moving in this direction. So up 3, left 4, that'll be a point on our line here. So let's plot that. Another point in the opposite direction. So here, what we'll do in this case is we'll move right 4, but then we'll go down 3. So that down 3 is accounting for the negative. So that there. And then continuing this process, we're going to get a couple more points in our line. Now in this example, we're looking for values that'll make this left-hand side of our inequality greater than or equal to 12. So when we graph this guy, we're going to use a solid line, indicating that the values on the line are also included. Okay, so in the last example, we used a dash line because we did not want to include these values, because these values on this line made this guy equal to 3. Now here on this case, we are looking for the values that'll make this equal to 12. So for example, if we were to plug in this point on our line, 0, 3, we would get a 0 for this guy here and a 3 for this guy. Sorry, we would get a 0 for our x and then a 3 for this guy. So this term would go away and we would get 4 times 3, which is 12, and that would be greater than or equal to 12 because it's equal to 12. So just trying to emphasize that everything on this line is going to make this exactly equal to 12. Now, we're also looking for the values that'll make this greater than 12. And so that'll be everything above this line. So all of our answers, all of our solutions are going to lie in this shaded region above our line. And again, we can pick a test point just to make sure that this is the case. Let's pick the point 2, 3 here. So we'll pick this guy. Plugging 2 in for our x here and 3 for our y, we can already see that this is going to be greater than 12. We're going to have 6 plus 12 here, which is definitely greater than 12. So that point works. All right, now for the next two examples, we're going to do something similar, but now we're looking at these compound inequalities here. For 42, we have 3x minus y is greater than or equal to 3, and y is less than 3. So we're looking for solutions that will satisfy both of these. Remember, we're looking at an and, so this is thought of as the intersection. We saw that from last week's material. So we're going to do the same thing here. We're first going to identify our boundaries, and in this case, it's going to be 3x minus y is equal to 3, and y is equal to 3. So this is actually the same equation that we saw in this question here, 16. 3x minus y is less than 3. So graphing this boundary, we know it's just going to be y is equal to 3x minus 3. And then we already have a line for this guy. So what we'll do is graph them. Our first equation is the same as last time. Our y-intercept is going to be -3 here. And our slope is going to be up 3 over 1. So this will be the line for our first equation here. And then the line for our second equation, let's do some color coding. First equation is this one here, and our second will be in blue. So that's y is equal to 3. So that'll just be this horizontal line here. All right, and then y is equal to 3 is going to be in blue, and the other one's going to be in green. Okay, so now for our first equation here, we're looking for all of these x and y values that'll be greater than or equal to 3. And then just as a side note, actually, what we're going to do is our first equation, notice it is a greater than or equal to sign. So we're going to keep this as a solid line. But for our second, we're going to use a dashed line because we're saying y is less than 3. So this is the boundary for that one. Okay, just to be consistent with how we draw these. Now for our first inequality here, we're looking for values that'll make this greater than or equal to 3. So this is going to be everything to the right and including this line here. And we can test this by picking a test point and making sure that it does satisfy that. Now for this guy, we're looking at all the y values that are going to be less than 3. So that'll be everything below our dashed line here, right? If y is equal to 3 is this line, then all of these y values are going to be smaller than that. Now, since we're looking at an intersection, we're saying that all of our solutions have to satisfy both of these guys. The only solutions we're going to have is where it intersects, so everything in this region. So I'm just going to label that and say our solutions lie here. All right, so all of the values in this region is going to satisfy both of these inequalities. Okay, and then we can test that. Let's pick a test point that's in this intersection. Let's pick this coordinate here, 2, -2. So we're going to plug this into both of our inequalities. We're going to have 3 times 2 minus a -2 needs to be greater than or equal to 3. This will be 6 plus 2 here, which is definitely greater than or equal to 3, but it also needs to satisfy our second inequality, y is less than 3. And we can easily see that it does. Our y value is -2, and we know that -2 is less than 3. So that satisfies it. All right, let's do this next problem here. For question 49, this is going to be very similar, but in this case, we're dealing with an or statement. So here, we're just looking at the union of our solutions here. So first thing we're going to do is, again, identify and graph our boundaries. In this case, it's going to be x minus y is equal to 1, and y is equal to 2. Now notice that both of these have a greater than or equal to symbol, so when we graph these, we're going to use a solid line for both. Now in this case, we want to solve for y, just so that it's easier to graph. Doing so, we're going to add y to both sides and then subtract our 1 here. So we're going to get y is equal to x minus 1. So in this case, our intercept is going to be 0, -1, so this point here. And then the coefficient of our x value is just 1 in this case, so our rise over run is just going to be 1 over 1. So more points on the line are going to look like this here. So graphing this and making it a solid line, we'll have this here. And then remember, we're including the values on this line. The values on this line will make this statement here true. For example, if we were to use our y-intercept, so 0, -1, we'd plug in a 0 for x and a -1 for y. This would give us a +1 on this left-hand side, which is in fact equal to 1. All right, so let's also plot this one here. This y is equal to 2. That'll be the horizontal line through the point here. And then just to keep up with our color coding. All right, so going back to our inequalities, we're looking for the values that'll be greater than or equal to 1. So for this one here, it's going to be everything to the right of this guy, everything over here. So we'll color that in green in this region. Now for y is greater than or equal to 2, it's going to be everything above this line 2, right? If this y value is 2 here, it's going to be everything above it. Now, since we're looking at the union of this, we're looking for all solutions that'll satisfy this one or satisfy this one. So our solutions are going to be everything in all 3 of these shaded regions. So we'll just say that here. All right, and for both of these, this one we were looking at the intersection, so we're only testing everything in this region. Now for this one, we're looking at the union, so you could take a test point in all 3 of these regions and make sure that it does satisfy. So the video got cut off, but we're starting on section 2.5. And for this problem, what we're asked to do is write this relation here, given in this table, as a set of ordered pairs. So in this table, we have these years here, and then for each year, there's a corresponding average ticket price. And so to write this as a set of ordered pairs, we are using a set notation, so we're going to use our curly braces here. And then we're just going to write each ordered pair. So for 1960, that's the input, and our output is this here. And then we repeat that for each of these input values. Okay, so that's how we did question 9. Now moving on to the next couple questions here, what we want to do for each of these is determine whether each relation is going to define a function and then give the domain and range. So for question 19 here, we again have a set of ordered pairs. Now looking at these guys, we can automatically tell that this is a function. And the reason is because each input value or each x value only corresponds to one output value or one y value. So we'll write that here. So each x corresponds to only one y. So this tells us this is a function. All right, now our domain is going to be all of our input values. So in this case, that'll be 5, 3, 4, and 7. And then our range is going to be all of our output values. So 1, 2, 9, and 6. All right, let's do the same thing for question 27 here. We're again given a relation, but in this case, it's given as a table. So these are all of our x, our input values, and these are all of our y, our output values. Now, automatically we can see that this is not a function. We have multiple input value, or we have one input value which corresponds to multiple output values. So this guy is not a function. And we'll say this particular value, x is equal to 1, corresponds to multiple y values. So that makes this not a function. Okay, we can still list its domain and range though. Its domain is going to be all of its input values, which in this case is just 1. And its range is all of the output values. So here, that'll be 5 to -1 and -4. All right, let's write this nicer. Okay, perfect. Now let's move on to 36 and 41. Again, what we want to do is figure out if each of these relation defines a function and then give the domain and range. Now in this case, we can easily figure out if a graph represents a function by using the vertical line test. And that test says that if we were to draw a bunch of vertical lines on a graph and it intersects the graph at only one point, then it would be a function. However, if it intersects the graph at multiple points, then it's not a function. So for 36 here, we can draw a bunch of vertical lines here. We can see that it intersects the graph at only one point. Each vertical line intersects at only one point. So this is a function. All right, now the domain is going to be all of the possible input values. And if you notice, that's going to be all of our x values. So looking on our x-axis, notice that these correspond to a lot of input values. And in fact, since this graph goes on forever in this direction and forever in this direction, it could be all of these x values or all of these x values. So we say that the domain, and we're actually going to write this in interval notation, is going to be from negative infinity up to infinity. So that big interval. Similarly, our range is also going to be negative infinity to positive infinity, and another way to say this is all real numbers. So this represents all real numbers. Now, by the same reasoning, we are going to get all of these y values and all of these y values down here, so that's why our range is also negative infinity to positive infinity. Now for question 41 here, we also want to figure out if this is a function, so we're going to use the vertical line test on this guy as well. So if we draw a bunch of vertical lines, we're going to get this here. But notice, this vertical line intersects here at 2 points, also here at 2 points, and same for this one. And in fact, if we only had one vertical line that intersected it at 2 different points, or more, then it would already tell us it's not a function. So this one is not a function, but we can still list its domain and range. So the domain here is going to be all of the possible input values. Now notice that this graph here, we're starting at x is equal to 0, and then all of the possible input values are moving in this direction here. So that's just going to be all of these negative x values. So our domain is going to be from negative infinity up to 0. So all of these positive x values are not going to be part of this domain. And then our range is all of the possible output values. And since this graph is going to go on forever in this direction and this direction, that includes all of these possible outputs and all of these possible output values. So our range, in this case, is also going to be all real numbers. For this next example here, we also want to identify if it's a function and find its domain and range. So we have this graph again, and so what we'll do is just use our vertical line test again. So we're going to draw a bunch of vertical lines, and notice that every single vertical line only intersects this graph at one point. So that means this is also a function. Now we just want to identify its domain and range. So this is going to be all of the possible input values. So the domain is going to be all of the possible values that we see here. And notice this is just going to be from -2 to +2. Okay? And then everything in between it. So in interval notation, this is going to be -2 to +2, and including those values as well. Then for our range, this is going to be all of our output values. Notice our y values are going to start from here, from 0 all the way up to this y value 4. We're not looking at the y values here or here. That's going to be outside of our range. So our range is just going to be from 0 to 4. All right, now let's look at these last two questions here. What we want to do is determine whether each relation defines y in a function of x. This should say defines y as a function of x, sorry. And then we want to give the domain here. So looking at 51 here, y is equal to 2x minus 6. This guy is going to be a function. For each x value, we're going to get a different y value. If we were to plug 1 in for x, we would get a different y value than if we were to plug in 2 for x, and so on. So this guy is going to be a function. And then we'll just write for each x value, we'll get a different y value. Okay? So no matter what, our outputs are going to change based off of what our x value is. Now, we can also justify this with a graph here. So if we were to graph this equation here, we would get this line here. Now notice if we were to use our vertical line test, this is going to intersect the graph at only one point, no matter how many vertical lines we draw, so this is a function. And then lastly, we want to find the domain and range. This is going to be all of the possible input values. Now notice this graph is actually continuing on in both directions here, so all of these x values and all of these x values are part of a domain. So the domain is going to be all real numbers, and then by the same reasoning here, our range is also going to be all real numbers. All of these possible output and all of these possible output values are in our range here. Now, let's look at one last example here. We have this guy here, y is equal to 7 over x minus 2. Now this one is also a function by the same reasoning here. No matter what x we plug in here, we're going to get a different y value. So this is going to be a function. And then I'll just write same reasoning as the last example. Well, if I can spell reasoning. Okay. But there's something super important to note about this equation here. So notice, if I were to take the value x is equal to 2 and plug that into this equation, we're going to get y is equal to 7 over 2 minus 2, which is the same as 7 over 0. Now remember, you can never divide by 0. This is going to be undefined. So this tells us that at that point, x is equal to 2, this function is undefined. So this value is not going to be in our domain. So in interval notation, our domain is going to be all values excluding x is equal to 2. So from negative infinity up to 2, but not including it, and then from 2 to positive infinity, and again, not including our value 2. Then our range is going to be all real numbers, and we can justify this with our graph here. So this is the graph of this function. What we have here is, as you can see, it's going to continue on in this direction, this direction, this direction, and this direction. But at this point, x is equal to 2, this graph is not going to touch this. And this is actually what's called a vertical asymptote, which we'll probably see later on in this section. But this asymptote is breaking down, or breaking up this graph here. So this point is undefined. This graph is going to go on forever in this direction and get super close to this line, but it's actually not going to touch this line. So this value, x is equal to 2, is not going to be in our domain. There's no output value that's going to correspond to that x value. All right, so that'll be it for this video.